give all the link to. So can you all see my screen now?
Yes, ma'am.
Both the previous classes I have uploaded on college LMS, and the Word file, the note that I have uploaded, that includes all these classes actually. I am not uploading the note separately because I have not separated it into class wise segments. It contains the entire thing that we are discussing, we have been discussing for the last few weeks, and we will be discussing for another week or so. Okay. So in our last class, in the last two classes, we saw how quantum mechanics came into existence, and why there was the requirement of a new kind of theory to explain things. And we saw that when very small things are observed, it is seen that they do not really behave like our regular observations in the macroscopic world. So there was a requirement of something new, and I also discussed why it is so important, because in today's age of fast communication and mini scale devices, quantum mechanics played a pivotal role in the development of this kind of technology also. And then in yesterday's class, in the last week's class, we saw how Schrodinger equation was developed. So I'll quickly recap this thing so that we can continue from Schrodinger equation. Okay. So we saw that from de Broglie's hypothesis, people understood that there was the requirement of a wave which is associated with a particle, because if energy is dual in nature, so must be matter. And then experimentally it was found that such a wave exists from the experiments with electrons and neutrons, deuteriums, etc. So then was the quest for the nature of this matter wave. And as I told you, that this wave cannot be a monochromatic wave starting at minus infinity and extending up to minus infinity, because that would mean that the particle can be anywhere between minus infinity and plus infinity, which is not the case, because we know that particles are highly localized entities. They have a certain position. Although in quantum mechanics there is an uncertainty in the position, but nevertheless that uncertainty is very small. So in our macroscopic world, we can always define a position for a given object, right? So an extent from minus infinity to plus infinity is not feasible. So they must be localized clusters, and you will study in your quantum theory and later on in this part also how these localized clusters are formed. These are called wave packets. But since it is a wave, therefore we can say that a wave equation, just like we have a wave equation for the electromagnetic wave, so a wave equation is required here too, to describe the motion of this wave that is moving along with the particle. So we saw that the one-dimensional wave equation is developed by considering a particle of mass m, which moves non-relativistically in the x direction, and it is moving under the action of force F, which is a conservative force. Okay. So the total energy of the particle can be written like this: kinetic plus potential. Now if you multiply this equation on both sides with the function psi, which we have considered to be our wave function, then since psi is of this form, psi for a plane wave, plane progressive wave, can be written in this form. Therefore, if you differentiate with respect to x once and then x again, you get something like this. Okay, so we are aiming at an expression for px square psi. All right, so that we obtain, and then if you differentiate with respect to t, then you get an expression for e psi. All right. So from these two equations, from the expression of px square psi in equation 2 and e psi in equation 2, we get, by substituting the terms, this expression minus h cut square by 2m del 2 psi del x2 plus v psi equal to ih cut del psi del t. Okay, so this, as you see, I have highlighted it. So this is the quote unquote Schrodinger equation, which is it is the basic building block of the entire quantum mechanics. It's the simplest form, of course. Later on, if you carry on with physics in your master degree, you'll see there are modifications and more complications to this Schrodinger equation. However, this is the basic building block upon which an entire science is resting. So you can estimate the importance of this equation, and as I told you in our last class also, that you have to know this equation like the back of your hand. There is no way where you can at any point of time from now onward say that I have forgotten Schrodinger equation. You cannot do that, because this is the basic building block of the entire uh, rest of quantum mechanics. Every quantum mechanical problem, you will have to start with Schrodinger equation. Okay, you have to start with Schrodinger equation. It's almost like Newton's laws of classical mechanics. Just like for understanding or finding out the trajectory of a particle, the first thing that you do is you write down Newton's second law, right? The differential equation, and then following the boundary conditions and the given situation, you solve it to get the trajectory of the particle. In the same manner, in quantum mechanics, you will first write down the Schrodinger equation according to the potential given, and then this is as you can see, the second order differential equation. So you will solve it and use the boundary conditions, and using that you will get the required wave function. Of course, there are other prescriptions that you need to follow, and that we'll know one by one in our discussions that will be following this. Okay. Okay. So now let us discuss the Schrodinger equation. This is the Schrodinger equation. Okay. Once again, I have sort of highlighted it so that you realize its importance. And definition, if you want to define or theoretically say what Schrodinger equation is. So this is the Schrodinger equation for a classical particle. Why classical particle? Because we have not considered relativistic movement. It is still moving non-relativistically. If you include relativity, there will be some more complications. And it is one-dimensional, so it is moving only in the x direction under the action of a conservative force field. So that is also a simplification, that the force field is conservative. If it is a non-conservative force field, then again there will be some complications brought into the equation. But as I told you, this is the basic building block, and on it the rest of the things will be developed. Alright. Of course, in 3 dimensions, it becomes like this. You replace del 2 del x2 by the Laplacian, and the rest of it remains the same. Psi now will be a function of rt instead of just xt. Okay, now if you consider a particle moving in the x direction and there are no external forces acting on the particle, then v is 0, so it is free to move. There is no forcing acting on it. Such a particle is called a free particle, and the time dependent Schrodinger equation for a free particle will be simply this. So you've got rid of the potential term because there is no force. So this is the simplest kind of Schrodinger equation, which is the Schrodinger equation for a free particle. Okay. Now Schrodinger equation is a partial differential equation. All this is recap. I already discussed this in our last class. So it is a partial differential equation, and if you can remember some of your ODE classes with TG sir in your first sem, then remember you used to solve such equations by the help of separation of variables technique. Okay. Since the potential is not a function of time, so we call x the time independent part and t the time dependent part, and therefore psi can be written as a product of x and t. Okay, so and of course for motion in 3 dimensions, then psi is a function of r and t, so it can be written as a product of r and t, where r is the position function and t is the time function. Okay, so in equation 6, that is in Schrodinger equation, we write psi as the product, all right, in the product form, and since del square is a space function dependent differential only, so t comes out, whereas this is a differentiation with respect to t only, so r comes out, and then if you divide it throughout by the product rt, then what you get is this, all right. So from here you can easily separate the time dependent and time independent portions, because V, as I told you, is the condition of separation of this equation is the condition that the potential is time independent, all right. So in the one dimensional case, we continue with psi as product of xt. So we divide by xt and get this. Once again, the left hand side is a function of x only and the right hand side is a function of t only. This is the time independent part and this is the time dependent part, all right. So each side can be equated to a constant. This is all differential equation technique. I hope this all of you can recall this. This is not new to anybody because all this has been done in your first sem mathematical methods classes. And this constant here is the total energy, because we know that when a particle is moving, when any object is moving, its total energy remains constant. There may be transformations in between, but the total energy will always remain constant. So if you take the time dependent part, then this is the solution you get by integrating. Take the time independent part, then this is the equation that you need to solve to get the expression of x, and this equation here that I have given a blue boundary, this is the time independent Schrodinger equation for a single particle in 1 dimensions. Okay, so you, yes, any question? Does anybody have any question? Okay, so this is the one-dimensional time-independent Schrodinger equation for a single particle. Okay, as you can see, whatever be the case, the time function, the time-dependent function will always be this. Of course, the boundary conditions will decide the value of this constant C1, but the form will always be this exponentially decaying function in T. The primary solution will be given by the time independent part, because that will be decided by the form of the potential V here, right? So this is really the equation you need to solve for the different problems of quantum mechanics. The corresponding solutions are called the time independent wave functions or steady state wave functions. Why steady state? Because as you can see, the time dependent part exponentially decays in time. So the time dependent part will quickly decay to very small values because it is an exponentially decaying part. However, this is not time dependent, so this will not increase or decrease with time. This will remain whatever it is and depend only on x. Therefore, the solution of this equation here, the time independent Schrodinger equation, are called the steady state wave function. So our quest will be for the steady state wave functions. Okay. So if you rearrange this equation, you get this. This is what you will need to solve. And since psi is the product xt, so we can write now psi as c1x e to the power minus I e by h cut t. So this is the actual solution. Using the expression of e as h cut omega, you can write this expression as x e to the power minus I omega t if the constant c1 is 1. Okay, so these are the solutions of the time dependent Schrodinger equations. Of course, this is a particular solution for a particular value of the constant E. So that will decide a particular frequency of the wave. However, in general, you know that for differential equations, you need to get the general solution, which of course is because of the fact that the different values of the energy E under different conditions will give you different such particular solutions. For each E you will get a particular omega, and so that each of those omega values will give you a different expression for this function x e to the power minus I omega t. So different values of E will give you different particular solutions, so that the general solution is a sum of all the particular solutions with arbitrary coefficients. So this is the general solution of the Schrodinger equation, the time dependent Schrodinger equation, right? Again, a very important expression. So whatever solution you are aiming at, this is the form that you will get, and depending on the boundary conditions, the values of C, the constants, will change, and you will get a solution required for the given problem. Okay. Now the three-dimensional wave equation, you write p square as px square plus py square plus pz square, the linear momentum, so that in the expression of energy you write this, and then since psi, the expression of psi becomes this in terms of the momentum components. Therefore, if you differentiate it with respect to x, you get this. Again, if you differentiate with respect to y and z, then you get the values of py square psi and pz square psi. And of course, E psi equal to IH cut del psi del t we already had. So using these, the three-dimensional wave equation, which we had written down earlier, now we get to see how we arrive at the three-dimensional wave equation. It comes out to be this. So instead of del 2 del x2, you have the Laplacian square. Okay, so this is the three-dimensional Schrodinger equation. Okay. Once again, if you are solving three-dimensional problems, which you will do in the next semester when you do hydrogen atom problem, then you will need to use this form of Schrodinger equation, not the one-dimensional. Now, how do we solve? We saw how we solve the one-dimensional case. How do we solve the three-dimensional wave equation? Again, by separation of variables. So we write now psi as r into t, function of space and function of time. So that we can write the Schrodinger equation in this form, and then this is the time dependent part, which gives the solution, once again exponentially decaying time function, and the time independent part can be written like this, so that the three-dimensional time dependent waveform is once again Cr e to the power minus I omega t. Alright, depending on the boundary conditions, you will get the values of the constants. Okay. Now that we know that this is the solution of the Schrodinger equation, this is the form of the solution, and we will need to address a particular problem depending on the given force under whose influence the particle is moving. We will get different forms of V, and the form of V will decide how we go about solving the differential equation, and the given boundary conditions will tell us how we get the constants of the solution. So using that, we will get the different solutions of the Schrodinger equation. So we now know the mathematics. It is nothing but simple differential equation solving. You need to know how to solve differential equations using separation of. You need to know how to get a particular solution and a general solution by summing the different particular solution. So all this, as you know, you have been prepared for in your mathematical methods classes in your Sem 1. So if you have forgotten by now, then please go through your mathematical physics lectures books to recap how to solve differential equations, how to go about separation of variables, and how to arrive at different solutions using boundary conditions. And then also a little bit about general solutions and particular solutions. Of course, in this course, whatever problem we address, I will derive the solutions in class entirely. So, and then you will get variations as your homework assignments. But you need to know the method. Like, you cannot forget the method of solving differential equations, right? So you need to keep that in mind. So my suggestion would be to brush through your differential equation notes a bit from your first sem mathematical methods lectures or books. So now that we have got the general expression of the wave function, that is a solution of the Schrodinger equation, and remember here the Schrodinger equation will give you the wave function, which is which wave function? We have to remember our motivation in doing this. It is the wave function that represents the matter wave, the wave that is representing a moving particle, according to de Broglie theory, who said that every moving particle is also associated with a wave, right? That was our motivation. So now that we have seen what the solutions will be like, let us see what is the physical interpretation of this wave function, right? What does it physically mean? We have got mathematical expressions. We have seen mathematics of how to solve and get the expression. But here we are not in a mathematics class, although quantum mechanics, as you will see as we progress, that it involves a lot of mathematics. In class, we are going to do probably more mathematics than you do in your math method classes. So it involves a lot of mathematics and long derivations. Excuse me. However, we also need to know, since we are actually in a physics class, that what is the physical interpretation. Okay. Now we saw that the solution of Schrodinger equations, psi of x, y, z, t or psi of r, t is a complex function, right? We got some constant into some function of space coordinates into e to the power I omega t. Okay. So the fact that psi is a complex function suggests that we must not attempt to give the wave function any physical existence that may be measured by instruments. We do not wish to see the waves. They do not have any physical existence because as you can realize that a complex function cannot be observed in our real world, right? So the fact that the wave function is a complex function decides for us that any attempt to try to observe it using an instrument would be futile. So we will not attempt to do that. Instead, we will try to find out what else can be measured about this wave function. If we cannot observe the wave function itself, what can we actually observe? All right. So our next question is, what do we measure? What is it that we attempt to measure experimentally in quantum mechanics? Okay. Now, since psi is a complex function, therefore we can always write psi is equal to a plus ib. We all know this. Any complex function can be written as a sum of the real and complex parts. Therefore, the complex conjugate of psi star, will be equal to a minus ib. Correct? All of you know this also. So, if you take a product of psi star and psi, that is, you try to get the modulus of psi and then square it. So, we define a quantity p, which is a function of x, y, z, t, as square of the modulus of psi or psi star psi. Then evidently from the above prescription of psi and psi star, this quantity p has the expression a square plus b square, which means that it is real, right? Since it is real, therefore it is measurable. So although the wave function itself, being a complex function, cannot be observed or measured by an instrument, however, if we define the quantity p as mod psi square, which is a square plus b square, then it comes out to be a real quantity, which is why it is also a measurable quantity. This is called the probability density. This function p, capital P, x, y, z, t, defined as psi star psi, is called the probability density. Now, what do we do with the probability density? Okay, we can understand that it is real and measurable, but then what does it actually mean? Now, this entity, the probability density, was defined by Max Born. So Schrodinger gave us the mathematics, but the physical meaning was given by Max Born. That is how to identify the wave function, what to identify the wave function with, what to think of the wave function in the physical world. It's a complex quantity. We can understand that there is a wave associated with a moving particle. We saw from our numerical calculations why we cannot see such a wave in the macroscopic world, because of the sizes. The lambda becomes so small that we cannot really observe it or think about observing it. Okay, just a second, just give me a second. I have to attend a phone call. Yeah, sorry, I had to attend a phone call. Okay. So, as I was telling you, that Schrodinger gave us the mathematics. He showed us how mathematically we can find the wave function and do the mathematics, get the form of the function, etc. But he did not tell us anything about what to think about it physically. What does it actually physically mean? A mathematical function um, really has no use if you do not give it a physical meaning, right? If you don't know how to do an experiment and find out at least something about that function. And evidently, Schrodinger equation's solution, which is a complex function, cannot be measured. So, this quantity, probability density, which is real and measurable, was defined by Max Born. Alright? And if you see in one dimension, then P is psi star psi, and this quantity P dx, Pxt dx, is defined by Max Born as the probability of finding the particle at a coordinate between x and x plus dx. Okay, so as you can see that we cannot measure the wave function, and if you are talking about a plane progressive wave, then the position of the particle becomes infinitely uh, uncertain. But here Max Born is giving us a quantity which will tell us that any particular instant of time, if you try to find the particle, then what is the probability that you would get it at a given interval between x and x plus dx. Okay, so if you can find out the expression of psi and then you find its modulus square, then that modulus square will give you the probability with which you will find the particle at any given instant of time within a particular interval of x. Okay, is this portion clear to you, or do you want me to repeat it once more? Because this concept is extremely important. You need to understand this. I mean, I don't expect you to understand it at once, but at least you should, for the time being, have a feeling of what I am saying. Otherwise, when you go back and read my notes or the book by yourself, you will be clueless. So have you understood what I am trying to say, or do you want me to repeat this once more? Please unmute and tell me whether you want me to repeat this once more.
Ma'am, repeat it, ma'am.
Repeat it. Okay. So as I told you that the wave function psi that we are getting by solving Schrodinger equation is a complex function. So there is no question that we can see it or measure it, because we know that a complex function is a mathematical concept, it is not physically measurable. But then what do we measure? So Schrodinger's equation is giving us the mathematics. It is absolutely necessary because whatever problem we get, we need to use Schrodinger equation to solve it, get the quantum mechanical solution and get the wave function. Very good, very good. But what do we interpret about this wave function, the complex function that we are getting? This interpretation was given by Max Born. What does it say? It says that, so suppose a particle is moving in the x direction, and at any instant of time we do not know where to find it. Alright, we've got the wave function, but we have no clue where to find the particle. So this expression, probability density, will tell you that at a given instant of time, if you look at this function, you will get something, some real quantity, a square plus b square. That real quantity, see if you plot a graph, then you will get some position of x at which this p will reach a peak value. So that position is the maximum probable position of the particle. So at that particular instant of time, you are you will possibly get to find the particle over there with maximum probability. Okay, so it is like, let me tell you, suppose you take two students A and B of your class. All right, now A is very studious. He always does all classes. He never skips any class. Um, and he's very serious about his studies. All right. Now B, I'm not telling about what their results are. I'm just telling you their personal behavior. A is very studious. He never misses any class, and he always, according to the routine, he will always do every class if he is in college. And B, on the other hand, is very irregular in his classes. He comes to college regularly, but he will probably stay in the union room, or sometimes in front of the canteen, or sometimes in Imami market, and he roams about here and there. Sometimes he does the classes, sometimes he skips the classes. He's not very consistent in his behavior regarding classes. All right. So if I tell a person that this is A's behavior and this is B's behavior. Now college timing is between 10 and 5, and this is the routine, class routine of physics Sem 3 honors. Okay. Please go and find A and B and bring them to me. I need to talk to them. All right. So person who gets this information that I have given him, he will, to look for A, say at a particular, when a particular class is on, he will see which room the class is in, and he'll quickly go to that room and he'll find A, because that is his maximum probable position. He does all the classes. So at a given time, if there is a class, he will most probably be in class. So he will quickly go to, say, in that, say this is third period and your class is in room number 602. So the person will quickly go to room number 602 and call A and tell him that man is calling. Easy for him. But for B, it will not be so easy for him. So he will have to, he may find B in class, but he may not also find B in class. So he might then look in the union room. He may find him there. He may not find him there. He may then look in front of the canteen. He may look in front of the in the driveway where the people, stand and gossip or play. So in this manner, to find B, this person has to take some pain. It is not easy for him to find B as easy it was for him to find A. Right? So the graph of finding, the probability of finding A and the probability of finding B are different, right? So this function P, the probability density, will decide how easy or not easy it is to find a particular particle which is following a particular Schrodinger equation at a particular instant of time within a space interval dx. If it is a regular function, then it is very easy to tell you where you will find the particle at a given instant. If it is not a regular function like B, then it will not be easy to find the particle at a given instant. There may be several places where it can be present at any given time. Okay. So now have you understood what I'm trying to say? What is probability density exactly? Is the picture a tad bit clearer than before? Can someone unmute and say yes or no?
Yes, ma'am. Totally clear.
Okay. Okay. So this is
Yes,
what.
ma'am.
Okay. So this is what probability. So now, so you can understand that Max Born is giving you a physical quantity which can actually be measured. Okay. So if you get a wave function, you can quickly find its modular square, and then you will get a quantity that you can actually measure. And then that measurement will tell you what the most probable position of a particle is at a given instant of time, and then you can look for it then. Okay, so this is the physical interpretation of the wave function. That is the solution of the Schrodinger equation. Alright? This entire thing is known as Born interpretation. What I have just now explained, this entire thing is called Born interpretation, and that is the physical interpretation of the mathematical form, that is Schrodinger equation. So both are equally important. Without the mathematics you would not get the physical meaning. Again, without the physical meaning the mathematics would really not have any essence. So both are equally important. Okay. Every book contains Born interpretation. The notes that I have given you, that also contains Born interpretation in detail. So please read through. Once again, I am telling you, if you have any questions, then do get back to me and do ask me in the next class. Okay, if you have any doubts, then in the beginning of the class, please tell me that, ma'am, this portion we did not, because this thing that I am taking the classes on now are extremely new to you. This is totally new. You've not done this before. And the interpretations are not very easy. They're pretty abstract. Okay, it's not like Newton's laws that you know the car is at this position at this time, so after some time it will go there. So it is not very easy for you to interpret. However, it is necessary because it is a part of your syllabus and it is a very important part of quantum mechanics.
এটি দেখে দেবে কেউ কলমের লোকটা দাঁড়িয়ে আছে আমার সাথে
So please read several times, and if you have doubts, you are sure to have doubts. If you say no, I have understood, I don't have any doubts, then you've probably not understood anything at all. So please clear your doubts by asking me. Okay, and if you really have time now that you are at home, if you want, if you have Resnick's book, then read it like a storybook. Okay, because Resnick has given Resnick and Iceberg, they have written down at one glance you would feel that why have they written so many things in a science book, but if you read that, it's like a story that makes you understand the scenario. All right, I myself read Resnick's book to understand what I need to say in class. So I miss having Resnick's book during my physics honors days, during my student days. Okay, so if you have the book, good. If you don't have the book, please send me a message in WhatsApp in your group. I will scan the pages required and send it to you in our group. No problem. Okay, but I need to know whether you need it or not. So please feel free to tell me whether you require it and send me a message in WhatsApp. I'll scan the required pages and send it to you. It's very, very good. As I told you, don't read it like a textbook. Read it like a storybook. The pages that they have written down without the mathematics. And the beauty of Resnick and Iceberg's book is that all the complex mathematics, they send it to the appendix. They just write, see the appendix for the mathematics. So if you need to know the mathematics, you go to the appendix and do the mathematics. but the physical meanings, the interpretations are beautifully explained in the chapters. So read, you must not take it like a textbook, uh, when you are reading it in your free time. Read it like a storybook. You'll understand the physical meaning. This is my suggestion. Okay. So this is Born interpretation, which is giving us something to measure about this wave function. Okay. So till now, experiments were done where the wave was found associated with particles, and now Schrodinger gave a mathematical equation like our Newton's second law of classical physics. Now we have a mathematical equation in quantum physics, solving which we can find the motion or direction or development of the wave function, evolution of the wave function. But Born interpretation also gives us something that we can measure, and by measuring that we can actually find out the particle at a particular instant of time, okay, or at least an interval within which we can find the particle. Okay. So once again I ask this question, what do we measure? We just found out that p xt dx is the probability of finding the particle between x and x plus dx at any instant of time t. Okay, this is the probability density. Now we will think of something else that we can measure. We consider identical systems, infinite number of identical systems, which are all described by this wave function psi. Okay, so this is a thought experiment which you have to think about hypothetically. Okay, so I'm telling you very slowly. Listen to it like a story. Consider several systems, like n systems, infinite number of systems, which all follow the same Schrodinger equation, so that the solution of all these are psi. Therefore, all these systems that I am talking about are all described by the same wave function psi x. Okay. Now suppose at any instant of time t, you measure the probability density on these systems repeatedly. For all the systems at a given instant of time t, you measure px dx. You have psi, so you can find mod psi square. So you know px dx. So at any instant of time, you keep on measuring p on all these systems. And then you take the average of all these measured values. Alright. So what are the three things that we are doing hypothetically? We think of infinite number of systems, identical systems, lined up, and all of them are represented by the same wave function. Then we measure the probability density of all these systems at a given instant of time. At one particular time, we are not time averaging. We are taking all the systems, and at one instant of time, we are measuring the probability density of all these systems. Then what do? We take the average of these measured values. We've taken the measurement, now we take the mean of all these values. The result that we get is defined as the expectation value. Another very, very important term in quantum mechanics. This again is something that you can measure physically. Okay? It's not a time average. It's an average over a number of systems. So you have n number of identical systems, you measure all their probability densities at a given instant of time, and then you take the average of all these measured values, and you define the result as the expectation value. So what is the mathematics of this? This is the symbol of the expectation value. Okay, this angled bracket x, if you're trying to find out the expectation value of x for a given wave function, then you can understand that if p is the probability density of finding x, then this average will be over minus infinity to plus infinity x px dx. But px is psi star psi, so we write the expectation value of x as minus infinity to plus infinity psi star x dx. The prescription is to write the quantity for which you are trying to find the expectation value in between, sandwiched between psi star and psi. Why this is done, you'll get to know in a few more slides, maybe in our next class. Okay? For the time being, just remember that this is a mathematical expression, and as you can see that it is a real quantity, it is not a complex quantity. Since it is a real quantity, you can measure it. Okay, so this is another thing that someone is unmuted. Can you please mute? Yes, thank you. So you can measure this quantity, and we have defined here it here for x, the position of the particle. Similarly, for any function of x, fx, the expectation value is given by this formula. Angle bracket fx minus infinity to plus infinity psi star fx psi x dx. Okay, this is defined as the expectation value. So we get two physical entities that we can measure. One is the probability density and two is the expectation value. Okay, so expectation value of position for a given wave function is this mathematically. So if you know the form of psi, then you can easily do this integration. Expectation value for potential for a given wave function. The particle is moving under the potential Vx. So its expectation value at any instant of time is this mathematically. So if you solve Schroedinger equation to get psi and you know the potential under which it is moving, you simply do this integration and you'll get the expectation value of potential. Expectation value of linear momentum. I should have written px over here. So again this psi p psi, there should be a dx over here. Okay. Psi p psi dx. Expectation value of total energy. Psi e psi dx. So whatever be the quantity for which you want to find the expectation value, this is the formula. Alright. You solve Schroedinger equation, you get the function psi, then you put it in the expression for expectation value and find the expectation value of the required quantity. Okay. So we have seen physically what we can find, what we can measure from the abstract wave function. However, we must keep in mind now that quantum mechanics can only provide predictions. Think about the terms that I'm using. Probability density, expectation value. When you expect something, you're not sure about it, right? We expect the vaccine of the coronavirus to come out this year. It was expected in August. Did it come out in August? No. It was expected in December. Is it sure that it will come out in December? No. So when you expect something, you give an exam and then you expect a 90, you get 85. Okay, you expect 90 and you get 92. So expectation is a probabilistic term. When I am talking about probability density, even when I was giving you the example of the students A and B, even though for A, it is sure that if he is in college, he will do all classes, even then, finding him in a particular room at a particular time is a probability. The probability is very high. For B, the probability of finding him in a particular room is very low. For A, the probability of finding him in a particular room in the time of a class is very high, but it is still a probability. So quantum mechanics can only provide predictions. In classical mechanics, when we used to solve Newton's equations, the second law, you get a deterministic value. The particle is at this and this position at this and this time. After so and so time, where will it be? So you get the exact value. It is deterministic. If I give you the speed of a car and I tell you the car is in say Exide crossing at 10 a.m., where will it be at 2 p.m. if it is moving say northwards? Mathematically you will solve and you will give me the result. But that is again the expected result. There may be traffic jam, there may be some breakdown in the car, there may be some other issues that might crop up in between, right? So these results, though it is not quantum mechanics yet, these are probabilistic values, these are predictions. Okay, in the Bihar elections, it was predicted that so and so party will win and so party will lose. So and so party will get so many number of votes. It's a prediction. So the world rests on predictions. All right. We are still predicting when we will resume our normal life, when our routine will become normal, when will we be able to step out into the open without a mask. And probably again, that might not come in any time in the future. The mask probably has become our, a constant in our lives. But as I'm telling you that everything is predictive. So quantum mechanics will give us only predictions. Okay? It will not tell us that a particle in a given energy state will be found at a precise location at a certain time. It will never be able to tell us this. If someone is telling you, oh, I've solved this equation, Schroedinger equation, and I'm telling you that the particle has this energy at this instant of time and it will be found in so and so coordinate, you can hands down tell him you're wrong. There is no certainty. It is all predictive. It is all probabilistic. Okay? It will give you relative probabilities that the particles will be found at various locations at that time. It will tell you that finding the particle at say x equal to some distance from the origin, say x equal to 2.5 centimeters from the origin is highest, and at say 5 centimeters from the origin is lowest. It will give you, it will get a probability density function px, using which you will be able to tell this. At various locations, these are the probabilities. Just like I told you the examples of student A and student B. Finding A in the classroom during a class time is highest. Finding B is very difficult because there is no such high or low. He stays at different places at different times. So the entire thing is probabilistic. And these probabilities or these predictions are statistical in nature. We have moved from deterministic science to stochastic science. And we have to remember from now on that although there will be results and there will be theories and laws, But all these are predictive. Nothing is for sure. Even the experiments that you do, in the same apparatus, you are finding out Young's modulus. One person gets 2.19, one person gets 2.15. Who is wrong? No one is wrong. You are within the error bar. There is an error. These are predictive. Alright? So quantum mechanics expresses itself as probabilities and not certainties. This is one statement that you must bore into your heads for the rest of your lives. You might then say that, ma'am, then why is it so important if it cannot give us certain results? Because the probabilities that it gives, the predictions that it gives are pretty accurate. It is on these predictions that the Large Hadron Collider is working. All these large particle accelerators in CERN and elsewhere are working. Space physics is working. It is on all these predictions. Predictions that it gives are pretty accurate. But at the same point of time, you must remember that these are all predictions. No certainty. Which is why we cannot say that an electron is a particle of defined boundary that moves around the atom, the nucleus in an atom. By now you should all know, I'm sure you all have, since you all are doing physics, you all have read some way or the other that it's actually a cloud. It's fuzzy. There's no defined thing. Okay? And everything happens within that cloud. The entire universe is resting on this. Okay? So I think I'll not start operators today because already a lot of new things have been, a lot of new information has been meted out, and let me wait till you process all this information. Okay? So I'm sure today's class has left you all a little bit baffled because very new concepts, but you need not worry because Feynman himself, if you read Feynman's book, the volume is the third volume in which he gives you quantum mechanics. The first thing that he writes as, even at the end of one's career, a physicist cannot say that he has understood quantum mechanics. I have not. Like Feynman says, I have not. So it's a learning process. It's very abstract, but nevertheless, you have to attempt to understand the senses, and I will help you as far as possible in understanding the physicalities, the meanings, the interpretations. You need to go through, read a lot, and get back to me whenever you have any doubt. Okay? So, if you want me to scan a few pages of Iceberg and Resnick, if you don't have the book, then I'll be happy to do that. Just inform me in the WhatsApp group, and I'll
Ma'am,
send
I
you.
have one doubt, ma'am.
Yes, bolo.
Ma'am, is there any update of SEM 2, ma'am?
Okay, doubt on that? No,
Yes, ma'am.
no update.
Okay, ma'am.
Okay, just a second. I'll stop recording.